from Credo. A friendly note from our legal team. Please make sure you read every word of it. So the dual TOR technology that's been commonly used within data centers. So this is something that we worked along with Microsoft. So currently, the way the racks are deployed today is you have a switch which is on top of the rack, and it's a single point of failure today. Microsoft actually did a study, and I've attached a paper about 2 or 3 years back, where they looked at all the fleet of TORs that they had and looked at the number of failures they had. So about 2% of their switches do fail in the first 3 months. And the way they've categorized is 32% of those failures were hardware-related failures, and 27% of them were related to power. The rest were mostly software-related failures that they've noticed in the system. So when a TOR fails, it's a single point of failure if you don't have dual TOR, and it brings down the complete compute. Even if it's for a few minutes, it completely takes all the applications offline, and which is cause of a concern when Microsoft's providing this as a service. There's a classic solution to deploying dual TORs. You have 2 NICs, and you use like the multi-chase MLAG solution that's been in common. Microsoft did deploy this and used it for about a couple of years back. They did have the system into the data centers, and now they've transitioned over. In this solution, you have a 2 NICs, so either a dual port NIC or 2 NICs into the server farm. There are a couple of issues in this. First is you need an inter-switch connection, which basically tries to coordinate between the 2 TORs to see who's active and who's dormant or standby. This requires a little bit of customization. They need to understand the workload of each application that's running on the server. Based on that, they need to decide how much of the traffic or how much of bandwidth they need to dedicate for this interlink switch. The other problem, which is a very common problem with the inter-switch link, is it's called the split brain problem. So if the interlink switch goes down, or there's a race condition, they try to figure out who's active, and that causes a very well-known split brain problem, and it's very difficult to recover from there. So there's challenges with this. The other solution is, the other solution that has been worked out is we have a hypervisor that is there to kind of virtualize the 2 NICs that's being present there, and then there's a vSwitch solution to do that. But now you move a little bit of the complexity of managing these stores onto the compute side. And generally, in networking teams as big as Microsoft, there is a network team and the compute team, and you want the dependencies between them to be as little as possible. The other solution, so the hypervisor, the problem with the hypervisor is it takes up MIPS. When we were doing 10 gigs and 100 gigs, it was probably okay. For the MIPS, it took up from the compute side. But as we go on to 400 gigs and 800 gigs, the amount of resources you're going to send from the x86 side is going to be super high. And it's difficult for them to, it's an expensive resource that they want to save on that. It also creates an unstable latency, and this really won't work for RDMA, which is the key use case that Microsoft wants to deploy, or any of the big hyperscalers want to deploy. There's another solution from Intel, single root I/O virtualization. And what this does is it takes the problem away from the hypervisor, or removes the hypervisor, but takes it to the guest OS. Now, the VM has to be aware of the NIC, and any problems that happen with the NIC or the TOR, the VM has to now manage it. And you also have custom drivers, which again have to be managed by the VM, and it's kind of the different configuration that comes up is very difficult, and now you push the solution onto the guest OS. So if you look at the different solutions, of course, all these are vendor specific, so that's another problem. And that means now vendor specific drivers have to be embedded within the guest OS or the VM that's being distributed by Microsoft. And this, of course, requires a lot of dependencies and management, which they've been trying to avoid. So when we were working with them, we kind of looked at the system and said, there's been attempts to made at solving this at the NIC side. There's attempts being made to solving at the host OS side. There's also on the dual TOR on the network side. What about the cable that connects all these together? So we've developed a special cable. That's where we call our switch cable. The intelligence of managing the switch between the 2 TORs, managing how the TORs are going to switch, is part of the cable. So how does it all work? A little plug on HiWire. So this is the 4 types of cable we have. The switch cable is what we will be specifically discussing on this topic, but we also have the cloth, the shift, and the span cables. These are copper cables, but they're active copper cables. They're not passive. They have a lot more intelligence in them. This particular switch cable, we provide them in 50 gig, 100 gig, and 200 gig. It's NRZ and PM4. We allow automatic switching. It's lossless. We can do switching between an active TOR to a standby TOR in less than 100 milliseconds. It's a common data plane, so we can do firmware updates from all across the lanes. Gearbox, effect translation, all's built into the cable. So let's look at what the cable looks like. So the cable has it's a 3-ended cable, and one end of the cable has our chip inside. The chip is a switch. It's an L2 level switch, and we do PCS termination and all the ends in there. So it's very easy for us. It's like a digital mux that's sitting inside the cable there. There is a software part of it, which is developed by Microsoft, but it's enabled in part of the Sonic, and they've open sourced it as part of the 2021 November release. I think it's been open sourced from Sonic side. So another issue that we tried to solve here was we wanted to isolate all the management from the compute side and have it all part of the network side. So this cable is completely managed from the TOR end. So summary, I mean, if you look at it, the legacy system, there were issues with the capability planning, the ISL, the split brain issue on the TOR, the V-switch and the SRIOV, and the switch solution we have doesn't need an interlink between the two TORs. It's all managed by the cable. There's no state held, so the cable can decide which one is active, and it can automatically switch in case of failure. So then there's no server involvement, which is what Microsoft was trying to avoid. So how does this work? So this is what the cable or inside the cable looks like. There is a NIC that's connected to both TORs. The cable's in the middle. So the NIC is always broadcasting all the traffic. NIC is always broadcasting to the active TOR and the standby TOR. So TOR A on the top is the active TOR. The TOR B is the standby TOR. And when the active TOR is failed in any case, the switch can detect it and automatically switch it. So if you look at the northbound traffic, it's getting transitioned always to TOR A and TOR B, but the southbound traffic, the switch basically acts like a mux, and it knows which is active, and the passive or the standby TOR's traffic is ignored. So this all works through ICMPI. It's a very common protocol. We try to work through all the common protocols here. So both the TORs are actually pinging the NIC, and they are broadcasting their ID. TOR A ping is forwarded to the NIC, while TOR B ping is dropped. NIC learns the TOR A's destination MAC, and it knows that it needs to attach that and send the address through that. When it comes to the northbound traffic, TOR A's forwards both the destination addresses, but TOR B's traffics are dropped by the switch. Sorry, TOR B drops the packets because it knows that the destination address is not this, it drops it. While TOR A's destination address or MAC address is attached to the packet, so it allows the traffic to go through. Let's look at some of the failure scenarios. So in case of a planned maintenance, if TOR A is down, or you need to be able to just upgrade the software for TOR A, TOR B proactively issues commands to the switch and says, I need to get in power. And then TOR B's MAC address is broadcasted. Its MAC address is attached to the packets. And then NIC updates the destination for TOR B. And then in this case, TOR B's packets are going through and TOR A packets are discarded. And the convergence time to do this is less than 100 milliseconds. Typically, it's about 50 milliseconds that we can do the transition. In case of, in case of a hardware failure, like a TOR failure or a link failure, the concept is same. If the cable's cut or the support failure, cable detects that there's a loss of signal from TOR A, and then it basically, cable will auto switch the failure to link B. So now TOR B's destination address is mapped to the packet, and then TOR A's packets are dropped over. In case of the third scenario, this is more of the software failure issues. It's on the Sonic OS. There's many of them that Sonic OS documents. There's about 26 scenarios in there. So when TOR B times out, so all the packets are being sniffed by TOR A and TOR B. And if TOR B sees that it cannot sniff or it cannot see any more traffic coming from TOR A, the cable will immediately do the mux, and then TOR A is switched off, and TOR B is made into an active packet, active TOR. And then TOR B's packets are mapped, and then the NIC changes the destination address, and then the packets from TOR B go through, and TOR A are discarded. So there's a bunch of software written by Microsoft. They've all open sourced it as part of the open source repository. As far as from the November branch, this is available. Anyone can download it. This is fully deployed and working in the Microsoft data centers. So the dual TOR actually brings a lot of the complexity away from the VM. There's new features that we plan to add. Because the cable has an intelligent chip, we can enable security functions in the future releases. And then, of course, there's speed shifting and different speed modes that we plan to enable. That's all. Any questions?
If it runs with the speed more than 1 gig, which is of course, I mean, because
currently it's deployed with 100 gig and 200 gig.
Yeah, but are there any so-called auto-negotiations protocols on the link between, on the, let's say, QSFP slot or something like that?
No.
Or not anymore?
No, the cable does most of the intelligence.
It must be like fixed without any. I mean, you have to configure a fixed speed, and it just synchronizes the servers on both sides.
The cable has the auto negotiation to do the speed management because we control both the ends, so we can negotiate the speed between our ends of the QSFP.
Yeah, I was just curious because if you on one side, let's say side B, you just do transmission TX, so you broadcast packets to both switches, but you just drop the link on the other side. So from the point of view of your servers from switch B, is it synchronized or it is just disabled?
Disabled.
Okay, so you cannot have any auto negotiation, otherwise the entire link would go down.
Exactly.
Okay.
Yeah.
So if I understood the concept correctly, the cable that you introduced there is an intelligent layer 2 switch, right?
It is, yeah.
If you add that, then aren't you just adding another single point of failure, or basically removing redundancy? Because I mean, in the scenario before, you had 2 cables that were both allowed to fail, 2 NICs on the server side that were both allowed to fail, and 2 top-of-rack switches that were both allowed to fail, and in any scenario you would still be able to switch. Now in this scenario, if your cable fails, so your switch in the cable fails, everything is down, and if the NIC fails on the server side, everything is down, and if the cable between your switch and the server fails, everything is down again. No?
That's true, but the cable, the TOR will detect if the packets are not there because it's sniffing traffic from both TOR A and TOR B, and it'll report back. But yes, it will. If the cable fails, yes, it's going to be a single point of failure.
So one other question. Since basically the cable now is somewhat intelligent, what troubleshooting and debugging capabilities do we have, or do we just have to, if something goes wrong, run and pull the cables out of, of the server?
No, the cable does have telemetry. You can pull in a lot of more data from the cable. You can pull it from any of the ends of the cable. It does give you a lot of stats that you can pull through. And the drivers for that are written in part of the NOS, part of the Sonic.
And one last question is, obviously adding all that intelligence in the cable means cost. How is the additional cost of the cable gets recouped by the business? Where, putting that more cost in the cable, am I able to save it from somewhere else, or like how does the balance work?
I mean, you save it past of you. You have to use a single NIC, and even dual port NICs are expensive. Plus the extra compute that you have to spend in just managing the packet flows and latencies between the two. That's saving there for you. I mean, there is a whole maths we have, but it's difficult for me to share here. But there is maths in there.
Thanks.
Okay.
So, is it possible to buy the cable?
Sure.
And how much is the cable?
I wouldn't be able to say the price, but we have Jay from our sales team. He can help you buy them. Oh, actually, Stordis is here. They can help you source any of the cables you want. They are our distributor for Europe.